All right. Welcome back, guys. So today we're going to do the section 14.5, the chain rule. So let us briefly recall what we have done for now. For the first section, 14.1, we have introduced the multivariable function. So you know the graph, the domain, the codomain, different concepts of a function. For the second section, we introduced the limited continuity, which is a basic property of a function that we can investigate. And that also occurs in your calculus one, where we are discussing the limited continuity for a one-dimensional version function. As for 14.3, we introduced the analogy of differentiation in a high-dimensional setting, which is the partial derivative. In the setting, we simply regard the variable that we are not interested by constant, and we differentiate the variable that we are interested, assume a usual differentiation in 1D. As for 14.4, we introduced the concept of differentiability and tangent plane to generalize the idea of differentiability to higher dimensional. So for now, we are mostly on the definitions and conceptual ideas. And today we're going to go deep into the arithmetic part of our differentiation section, which is the chain rule, right? So since I prepared a lot of example in this slide, so this might be a long video. So yeah, just take your time and look through each examples. Right. So yeah, let us recall the one variable version chain rule. If we compose it to function by f circle g, so that is again recall what is f circle g. The function f circle gx is simply defined by f of g of x, right? So this is a composite function, and the differentiation of that function can be interpreted as this guy. F circle g prime of a is given by f prime, so you differentiate at first, you plug in g, and then you multiply by g prime of a, right? So it is called a chain rule in the sense of we sort of chain the composite function together, f prime and g prime, in that order, right? We can almost deal with the same idea in the multidimensional version of chain rule. So let us see this kind of taste of the formula. We will present, I think, two versions of chain rule. They all reduce to the same kind of formulation, but I want to do this step by step so you guys can not be sort of complicated by I don't know how to say this, like sort of missing the complicated notation, but we can start from the very basic example first. So again, I can generalize this to multi-dimensional space, but I first assume that we are working with two variables. And I just realized that I didn't give my notation here correctly. So wait a second. Let me, as always, this time I forgot to write something. Okay, so the domain is R. The domain is some domain, two variable domain, and it is a function value. It is a number valued function. So the codomain is R. We assume that it is differentiable at some point, x of a, y of a. I will introduce x of y soon enough. So those are defined to be you can think of them as a curve or simply a one-dimensional version function. So x are our functions from R to R. So you can think of maybe x of t to be, say, t squared, y of t, say maybe sine t, right? Those are just simple one-dimensional version function. And if those are differentiable as a one-dimensional function, then the differentiation of this composite function. So be careful, note that the composite function here is a little bit different from this guy. It is a composite function between a 2D function together with two 1D function, okay, x of t, y of t. So this guy is actually a one-dimensional function in the sense that it only has one variable, which is t. So I'm claiming that this differentiation, the differential of this guy at the point A is given by fx, which is the partial derivative of f with respect to x, plug it in the point x a y a, multiplied by the derivative x prime of a, plus fy, the partial derivative in the y direction, x a y a together with y prime of a, right? So a more useful notation is to write things down like this originally. So ddt is the one-dimensional derivative, right? I use d instead of partial. And then we have f circle xy. So again, xy is basically sending a variable t to two variable x of t, y of t, and then we send it using f to be f of x of t, y of t, right? So the whole composition is simply sending a number to a number in the usual sense in the one-dimensional function. So this function has derivative being partial f partial x, which correspond to this part, and dx dt, which correspond to this part, together with this two guy. Okay, so it looks a little bit different from our usual one-dimensional version chain rule, but we can see soon why this is the case. So now let us prove this theorem, which is kind of intuitive from definition. So first of all, what is the definition for a derivative of this function at the point A? You simply find out the difference between f of x dyt and f of x a y a, right? Divided by t minus a. This is the slope of the second line, and we want to approximate a tangent line, so we move x towards a, sorry, t towards a. And now we do some trick, which is we want to exploit the definition of differentiability here. Because f is differentiable, so I add these two guys, this blue guy and this blue guy, and I divide and I obviously have to, I'm subtracting these two guys here, right? So I'm adding them back and a limit at the end, right? So you see that I subtract this guy divided by t minus a, so I add this guy back by t minus a. And also the same thing happens for the y coordinate. And why do I want to do that? It's because that this is basically the tangent plane that we have learned in the previous video, the differentiability and tangent plane section, right? And let me just do some connotation that it is L of x t y t, where L is simply the linear approximation, if you guys remember from the previous video, of this function f at the point x a y a, right? And now, why is this kind of trick useful? So first of all, let us see this guy, the numerator, is simply f of x dyt, subtract by L of x dyt. And we want to, again, explore the definition of differentiability. So I divide it by the difference between the 2 point within the function, the argument. So x of t, y of t, minus x of a, y of a. But obviously I cannot do that. I cannot take that for granted. So I put an extra term here. So this two guys cancels out, right? And t minus a is still here. Whereas this point, this is actually what we want. You see that this guy does not depend on t, so we can just factor it out of the limit. And by definition, the limit of this guy is actually x prime of a, right? The same thing holds for this guy. You have fy, xa, ya, and y prime a. So you can see that the job here is to simply show that this whole thing is zero, right? However, this is actually very straightforward from definition because by definition of differentiability, this guy goes to zero as t goes to a, right? Since this guy converges to this guy, the point converges to that point. And so this will converge to zero by the definition of differentiability. Similarly, this guy actually looks like this. So you can see that by definition of the Cartesian distance, the Euclidean distance. This is x of t minus x of a squared together with y of t minus y of a squared. And by removing the t minus a inside the square root, you get this guy and this guy. But those are stable in the sense that it does not blow up. So it does not have anything to do the zero here. I want to emphasize here that even if we get a zero here, it does not automatically means that the limit is zero because this thing might blow up, right? As you see in the calculus one, there might be some indeterminate form like 0 minus times infinity, and in that case, you cannot determine a limit by this simple algebra. But in this case, this guy actually converges to a constant like this, x prime of a squared plus y prime of a squared. So 0 times that is obviously simply 0. And so we get the idea of the derivative being this chain rule flavor term, right? So let me go through this proof real fast again. Basically, what we're doing is, again, to apply the definition of differentiability. So I include the terms that makes the fxaya here the linear approximation, a first order approximation of the function at the point A. And coincidentally, the extra term here is actually just what we want. So at the end of the day, we simply have that the composite function f circle xy taking derivative at t is simply partial f partial x dx dt, partial f partial y, and dy dt. Right? So those are the proof, but again, the most important thing is the example. So let us try to do this. So given z to be 1 plus root x, 1 plus xy taking square root, and where x is tangent t, y is inverse tangent t, or arctangent t, we want to find the differentiation of z respect to t. So again, you can try to do this by actually composing tangent t inside this guy and inverse tangent t inside this guy, and then differentiate it using the one-dimensional calculus. But now we have the powerful tool, which is a chain rule. Let's do this. So dz dt will be partial x, partial z, partial x, dx dt, together with partial z, partial y, dy dt. So the idea of this kind of memorization is kind of simple. You always differentiate respect to some variable that appears in the last part of the differentiation. And you have some intermediate variables that you want to do respect to the first function here. Okay? And then it's just the algebra. So we know that taking a differentiation of z respect to x gives us, using the usual chain rule, you regard y as a constant, right? So differentiating respect to x gives you 2 square root of 1 plus xy in the denominator. And the chain rule gives you that the differentiation of xy respect to x is just y. And we want to plug in the xy being tangent t and inverse tangent t at the end, because eventually z should be a function in terms of t. And then what is the differentiation of x respect to t? Oh, sorry, this here. You simply get second squared t, right? That's the usual calculus to algebra, I think. And the same thing happens for partial z, partial y. You get a symmetric formula. And then you have the differentiation of inverse tangent to be 1 plus t squared in the denominator and 1 in the numerator. So, and then do some algebra. Actually, this will be sufficient, but actually do some algebra, you will get this guy, okay? I want to emphasize that this guy does not go to 1, right? Tangent t and tangent t inverse are inverse functions, but not reciprocals, so be careful with that. But anyway, that is how we apply a chain rule to a multidimensional function composite with a bunch of one-dimensional functions. And now if we want to generalize the chain rule, we can actually composite it with a multidimensional function. So a multidimensional function composite with multidimensional function. And if that makes sense, then we can do a differentiation. So again, let us take the theorem. If f is some differential function at some point xy, and x and y are itself two variable function, t and s, then a composite function, f circle with xy. So let me again emphasize this. What is f circle xy? So it is, in general, this guy, okay? It is actually a function of two variables, t and s. Given t and s, you have x and y. Given x and y, you have f. So it is a two-variable function. So that two-variable function can be partial derivative differentiated with respect to t and s. And the formula is quite similar to what we have just done. So you have partial f, partial x, and partial x, partial t. In this case, we're doing partial. Be careful. This is different from the previous version because in the previous version, x is a one-variable function. So it's dx dt. But now x is actually a two-variable function. So partial x, partial t. And the same thing here, partial f, partial y, together with partial y, partial t. The same thing happens if you're differentiating with respect to s. So this is a diagram of how the whole function actually works. Given st, we have by xy, you have a two-variable argument. You plug it in f, you get some argument z. Sorry, you get some output z. So z is a two-variable function with respect to s and t. And this is actually nothing but a generalization of the previous theorem, because dealing with the partial differentiation, you're simply regarding the s here to be constant, right? So everything reduced to a one-variable calculus. So this is nothing really special. It is just a generalization of the previous theorem, actually a direct generalization. So again, this is a little bit hard to see from the formula, but let us try to do the algebra once. So in this case, I set z to be e to the r cosine theta. where r and theta is itself the function of s and t. So r is st, and theta is square root of s squared plus t squared. Now we want to find partial z partial s and partial z partial t. So first of all, again, by chain rule, we know that partial z partial t is partial z partial r partial s. So again, note that these variables here are the variable in z, and this variable is the variable that we're differentiating. Okay? In case that you don't know how to memorize this. So now what is partial z partial r? ER differentiated by r is simply ER, so you get the same thing. And then partial z partial theta is here. It is ER minus sin theta, right? And obviously we have to plug in the corresponding r and theta. As for the second derivative term, the differentiation of r respect to s is t here. And differentiation of theta respect to s is here. S divided by s squared of s plus t squared. When I'm dealing with one-dimensional differentiation, I will go kind of fast, but if it does not make sense to you, please let me know, all right? And then it's just algebra. So after some combination factoring out, you get this guy, right? The same thing happens for t. So if we want to differentiate z respect to t, we get partial z partial r partial t, partial z partial theta, and partial theta partial t. So again, the differentiation of z respect to r is the same thing, and the differentiation of z respect to theta is the same thing. The different thing is that we are multiplying by r differentiated by t here, so we get s instead of t, and we are multiplying partial theta partial t here instead of partial theta partial s, so you get t over square root of s squared plus t squared instead of this guy. And then again, by some algebra, you get what we want, right? And obviously, it is generalized to even higher dimensional. For example, if in this case, these are a three-variable function, say TSU, then you can again do something like, actually, it is almost the same formula. Partial u, it is partial f, partial x, partial u, plus partial f, partial y, partial u. Okay, it generalized naturally. And I didn't write down the exact formula here, since that it does not really make sense to just write down an abstract notation. I will recommend you try to do that algebra in different exercises to see that everything generalized to higher dimension. And it's in a natural sense. We don't have to really write down the exact abstract formula. It does not really increase your understanding, I would assume. Okay, so here's an example that is not really important. So if you don't want to see this, just skip it. This is an example that I want to demonstrate to you why is this kind of chain rule important and how it plays a role in the partial differentiation equation theory. So given some function z, it is a two-variable function f of x, y. Now we translate it into a polar coordinate. X is r cosine theta and y is r sine theta. So in this case, you can see that x and y are both functions for the r and theta, right? So this reduced to our previous chain rule, which is that we're composing two variable function with one two-variable function. So it is f of x r theta, y r theta. And we want to show that the second derivative of z respect to x and the second derivative of z respect to y can be given by this formula. So this is actually a really nice identity in the sense that the left-hand side here is a very useful operator named the Laplacian. So if you guys recall, we have introduced this in 14.3 in a partial derivative. Let me see. It's in some example here. Yeah, so I've defined the partial derivative here to be the addition of each second derivative with respect to each coordinate. So in this case, we're simply considering the case where n is 2. We're dealing with two-dimensional functions. And we're saying that it can be reduced into the differentiation with respect to r and theta in terms of this guy, and this guy. And the useful feature here is that when we are solving this equation, when we're solving whether some function has Laplacian 0, Then we can reduce it to polar coordinate and to verify that whether it is zero under this kind of notation. And it is in particular useful in the sense that most function that we anticipate to be the solution should be kind of radial symmetrical. So it should behave the same on each R, on each data, and the only difference is in the R. So that's why this is kind of useful, because reducing the function in terms of R and data in terms of polar coordinate usually simplifies the calculation. And again, as I mentioned, this example is not really important. I just want to demonstrate how chain rule is applicable to this kind of theory, and that I try to demonstrate some of the abstract computation, so you guys are more familiar with the abstract formulation. Okay. So let us restrict ourselves to the interval within the first quadrant. It is also doable for the second, third, and the fourth quadrant, but as I mentioned before in the supplement video for 14.2, I think, the polar coordinate thing, we'll have to add a correction term. And that is not always pleasant to write it down. So I'll just assume that the correction term is zero, which is that we are in the first quadrant. So R here is actually a function of x and y, right? We can write it down as this x squared plus y squared taking square root. That's a distance between x, y, and the origin, where theta can be written down into inverse tangent of y over x. Now we're trying to evaluate the derivative of z to x, right? So let us first compute what we have here. What is the derivative of r respect to x? We have simply this guy. And if you do that differentiation again, and you be careful with the algebra, you get this guy, okay? And the same thing happens for y. For theta, you have to be a little bit careful. So if you differentiate this with respect to x, you will get 1 plus y over x squared. And then you multiply the chain rule term, which is minus y divided by x squared. And then you get this formula here. And almost the same thing happens for y, but it's not entirely symmetrical. So if you differentiate this with respect to y, then you'll get again 1 plus y over x squared. But the chain rule term is kind of simpler. It is simply 1 over x. So eventually you'll get this guy. And the same thing happens if you do the second derivative, right? Okay, so now having those information, we can start our computation on the second derivative, which is very, very painful. But I just want to try to let you guys see that we can actually carry out everything here abstractly. So if we're computing the differentiation of z respect to x, according to the chain rule, that is simply z to r, r to x, z to theta, and theta to x, right? And then the second derivative of x is simply the second derivative of this whole thing. Now, I'll perform this whole thing without substituting everything. For example, we already know this guy, right? But I'm not substituting anything yet. I want to first simplify the formula and then substitute the actual derivative inside. So let us be really extremely careful with this. If I'm differentiating this guy, then this is the product, right? So we use product rule. We want to differentiate this first, multiply the latter term, differentiate the latter term, and multiply the first term. The same thing happens for theta. So you have this differentiation, nothing happens, this differentiation. Okay, and then we have to again apply the chain rule once again, because we're differentiating z is regarded as a function of r and theta. So you have z respect to r squared, and then r respect to x, whereas z respect to r and theta respect to x. And this term is the same, right? And then this term we can just give it here. It's enough. The same thing happens for theta. So the first term here can break down into two terms due to chain rule again. Okay, now basically we're simply done. So you see that is the differentiation of z respect to x in the second order, right? You can do the exact same thing for y. You can just replace everything x by y. So for example, what terms is contained in the coefficient of the second derivative of z respect to r? You have this guy right here, and you also have the y term. So you have this guy. And what contains for this mixed derivative, the second partial derivative? You have this term and also that term respect to y. Similarly, for the second partial derivative respect to, here, for the second partial derivative of z respect to theta, you get this thing squared, right? So you have this thing squared and this thing squared. Now for the first derivative, for the respect to r, you get the square term, and also that for y. Lastly, for the z theta, the first derivative, you have this guy. So you have a corresponding guy for y. So this whole thing will be our Laplacian, okay, in terms of r and theta. And now we plug in the coefficients. So this guy, by our previous calculation, is this guy. This guy, by our previous calculation, is this guy. And now the nice thing happens. The denominator is simply x squared plus y squared, right? The numerator is coincidentally x squared plus y squared. So that gives us 1, independent of what x and y are. And this guy vanishes due to the asymmetrical property of the differentiation of theta. And the same thing happens here. It's also 0. And we can do the semi-algebra for the rest of the two terms, which gives us this formula. Okay, so this is the identity that we desire, which is a very, very beautiful identity that tells you the relationship between a Laplacian in terms of the polar coordinate. And now I want to do some application. So let us go back to where we introduced the partial differentiation Laplace equation. I want you guys to show that the ln x squared plus y squared is actually a solution to the Laplace equation in two-dimensional version, right? And let us verify it here again. So u of xy being ln of x squared plus y squared is simply ln r squared, which is 2 ln r, right? So this is what I'm saying. This function are radial in the sense that it does not really depend on the angle. The value of this function is the same of each circle with the center origin. So if I want to show that this is 0, I can apply in the presentation of the polar coordinate towards this function. And you can see that, for example, the first derivative of this guy is simply 2 times 1 over r, right? And if you do the second derivative, you'll get minus 1 over r squared. Whereas if you do a differentiation with respect to theta, you'll get 0. So everything becomes this guy, and then goes to 0. So you see that in this case, it is much more simpler. Obviously, we have done a bunch of algebra here, but after that kind of algebra, you see that it is a very nice operator in terms of the radius and the angle of theta. And that this is actually 0, making this a solution towards the Laplace equation. Okay, so that is a very complicated example. Now let's do some concrete function example. So in this case, I want to demonstrate you guys that the chain rule can be generalized to multidimensional. So I set up w to be xy e to the y plus z. So this is a 3-variable function where x is given by some 2-variable function, s plus 2t, and so is y and z. And I asked you to find the differentiation of z respect to t. So yeah, according to chain rule, in this case, the 3-dimensional chain rule, you have w respect to x first, w respect to y, respect to z, and then you have the corresponding, oh, wait, I'm differentiating respect to s, so let me change it to s, sorry. Should write t. Okay, so we have x to s, y to s, and z to s. And then it's simple calculus differentiation. The derivative of w with respect to x, according to, oh, you don't need any rule, but it's simply this guy, right? And you plug in the corresponding x, y, and z. And the derivative of x with respect to s is simply y. And you can perform this type of argument for the rest of the two terms. For example, in y, you have to apply the product rule because there's two terms here, y and this guy, right? So for the first guy, you have x times e to the y plus z, and the second guy does not change on the differentiation. So you get the same thing, xy e to the y plus z. And yeah, basically that's what we're doing. So after combining each term and performing some algebra, you get this nice differentiation, right? Okay, so this is just an example demonstrating that we can generalize this type of chain rule argument to 2-dimension, 3-dimension, n dimensions. Okay, so now we have introduced the chain rule. We have a really nice theorem that is called the implicit function theorem. So this is sort of an analogy of what you guys have learned back when you were doing implicit differentiation. So let me briefly recall what that is. So given a function, say x squared plus y squared plus xy equals to 1, we want to differentiate y with respect to x. So what does that sentence mean? Because this is an equation, right? I didn't write y as a function of x. But this is actually a curve. So curve. So locally, y looks like a function of x. So we can differentiate it, right? And then you can, by regarding y as a function of x, you can do a differentiation, d dx, respect to x, which you get something like 2x plus 2y, y prime, plus y plus xy prime equals to 0. And you can solve for y prime in terms of x and y. So that is called implicit differentiation. And now we want to formularize that kind of concept by this very nice theorem called implicit function theorem. This is a very, very important theorem in calculus and actually in real analysis. I won't prove it here. It is a little bit difficult to prove, so you guys can see the supplement. And let us first understand what this theorem is stating. That is the important part. So first of all, let us assume a two-dimensional function is continuously differentiable. So this is a new term here. By that, I simply mean that both partial derivatives are continuous. And then, sorry, by the way, this also implies differentiability, right? We have seen that in the previous video. And then, suppose that the point AB is such that f of AB is 0, and that the partial derivative of f respect to y is non-zero at the point AB, then I'm saying that y can be basically what we're gonna say here is that y can be locally solvable in X, in a sense that we can find a small interval a plus epsilon, a minus epsilon, a plus epsilon near a, so that there's a function f which is a solution for y. So I'm saying that y can be solved as f of x in this context. And I'm saying that this guy f of x actually satisfies f of x equals to 0. So if we're considering a level surface, this is this is a level curve. It is a one-dimensional thing, right? So I'm saying that you can find a function y equals f of x on that curve so that this happens, right? So, okay, let me maybe draw a graph. This is f of x, y being 0. Then at some point, you can always find y equals f of x so that you can represent this part of the um, variables by x, f of x. Okay, it is locally a function. Basically, that's what I'm saying. And also, this is the important part that the f here, the little f here is actually differentiable, and the derivative is given by the partial derivative f of x, fx here, divided by fy here. And again, sorry, there is a minus sign here. That is very important. Let me put it here. I don't know why I didn't write that. Okay, so it is minus fx divided by f4. So in a better notation, perhaps it is saying that, should I check the color? Let me check the color. Okay, so I'm basically saying that the differentiation of y respect to x on that curve, fxy being 0, is given by this guy. Okay? Right, so let us first understand what this theorem is saying. I will soon provide an example so you guys have a better understanding. But basically, we are saying that if the derivative with respect to y is non-zero, then the curve is locally solvable. We can solve y in terms of x, and then we can differentiate y in terms of x, and the formula is given like this. Now, that is a powerful theorem in the sense that we don't really actually know what y looks like, but we can perform algebra and calculus on that function. That is why this theorem is powerful. As I mentioned before, something like this function is actually not solvable in the sense that you cannot solve y, or maybe if I increase it to a very high power, it'll be very difficult to solve. And if it contains something like transcendental function, then it is even harder to solve. So we don't wish to solve the function itself, but we wish to present the function in this abstract sense, but we can also perform calculus on that. Okay? Right, so maybe I would say that an example is better to understand what that theorem is actually saying. So this is a very classical example. Given a function given by x squared plus y squared minus 1, so we know that a level curve, this level curve is simply a circle with center 0 and radius 1, right? So now we're interested in whether y can be solved locally in terms of x on this level set. And basically what I'm saying about this level set is just this rest. Okay? So according to the implicit function theorem, if I want to solve for y, then I have to differentiate this guy by y and see whether it is 0. So basically, I'm saying that this is non-zero whenever 2y is not 0, so y is not 0, so it is not this point and this point, right? And other than these 2 points, this part of the y and this part of y are actually solvable. So implicit function theorem states that they are solvable. It does not give us an actual solution. It just say that there is some solution. However, in this case, we can actually solve for y because this is quite simple. Y is simply square root of 1 minus x squared in the upper semisphere and minus square root of 1 minus x squared in the lower semisphere, right? So this is a good case where we can actually solve it. But in most cases, we don't actually have a formula for the solving for y. So that makes the implicit function theorem so important. Then even if we don't know the formula, we can still operate calculus on the solving function, the differentiability, basically saying. Okay, so according to this kind of diagram, why is this condition that important? You can see that why are these 2 points unsolvable? Why can y be represented as a function near the point where y is 0? And you can do a very simple guess, which is that anywhere near this part, the curve does not pass through the vertical test, right? In a sense that if you give some x, it will always be 2 values of y. So near this point, you can never find a small interval so that this curve is a function. However, if you are not dealing with this point, but some point that is close to this point, then it is good enough. You can find this very small interval that is actually a function which passes the vertical line test, and it can be represented as a function of x. So that is the uniqueness of this 2 point. Since the derivative is 0, it is locally not invertible, right? And now, according to our implicit function theorem, you can write down the differentiation in respect to x of y, which is given by minus fxx f of x, fyx f of x. And don't be frightened by this notation. F of x is simply y, right? So for instance, the first derivative of this guy with respect to x is 2x. So you have 2x in the denominator, and then 2y in the 2x in the numerator and 2y in the denominator, which is minus x over y. This is what implicit function theorem gives you. But now if we actually have the formula for this guy, you can differentiate it, right? So you get the same formula like this when y is positive on the upper hemisphere, and this when y is negative on the lower hemisphere. So this is the case where we can actually solve the function y. And this is the case where we cannot solve for y, but we can represent the derivative as a function of x and y. Okay. I hope the example help you guys understand how powerful implicit function theorem is and what it actually means. And yeah, so this remark here, the first remark is what I just mentioned. The importance of the implicit function theorem is the existence of such function and the fact that we can actually perform calculus on that function instead of knowing what that is. That is kind of mystery, right? We don't know what that is, but we can evaluate the differentiation of that guy. And the second thing is that obviously generalized to higher dimension. I just performed the 2-dimensional version because it is better to understand. But the multi-dimensional version is actually quite similar. So let me state the theorem. Again, if you're on a level set f of x, y, z being 0, and that at the point ABC, the z derivative, you can represent it by x and y, is non-zero, then z can be locally solved in terms of x and y, and that the differentiation of z respect to x is minus fx divided by fz, and the differentiation of z respect to y is fy minus divided by fz, taking a minus signature. Okay? So again, the important part is the example. So let us do some example. So first of all, I want you guys to find a tangent line to the curve y cosine x and equals to x plus y squared at the point 0, 1. So let us first fix this back to the implicit function theorem setting. So if we set f of xy to be this guy, which is simply subtracting this to here, then this is basically saying fxy to be 0, right? And just to note that this is an example that we can actually solve for y because there is some transcendental function. You cannot solve y equals to something, something, something. Okay, technically you can because this is a quadratic equation, but it'll be highly complicated. If I put something like this, then it'll be not trivial. Okay, but anyway, we can verify that at that point, f01 is actually 0, meaning that this point is actually on this curve, and that the differentiation with respect to y is actually non-zero at the point 0, 1. So by implicit function theorem, y is locally solvable, or that y is basically some function of x near the point 0, 1. And that the derivative is given by minus fx divided by fy, where the numerator, where numerator is 2, uh, is 2, why am I writing this? 2x. Oh, sorry. I put an extra x here. Okay, sorry. So the differentiation is correct. It is 1 plus y sine x, and the denominator is 2y minus cosine x when we differentiate with respect to y. And if you plug in 0, 1, you get minus 1. So minus 1 is basically the slope of the tangent line, right? So you have y minus 1, the 1 comes from here, time equals to minus 1 comes from here, x minus 0, 0 comes from here. And the graph is looked like this. This is f of xy being 0. That is actually a very, very straight curve. And the tangent line looks like this. So this is what I'm saying, that even if you don't know what y actually looks like, in fact, you can try to solve this. Y is some very complicated quadratic formula thingy. And you can differentiate that to find out that the derivative is actually this guy. And also that to avoid that such a complicated algebra, this kind of implicit differentiation is very, very useful. And that we can actually find a tangent line, which is a sort of a first step of analysis on this function at the point 0. Okay. And we can do the same thing for higher dimension. So if we're considering this function to z equals to xyz, the point 2, 1, 1, I want to investigate the tangent plane at the point 2, 1, 1. Now let us see what we can do. So again, we set f of xyz to be in the setting as the implicit function theorem. So this guy being 0 is basically the equation here, right? So again, we verify that this is actually on the surface, and that according to the differentiation respect to z is non-zero at the point. So let me emphasize here, you don't really have to always do z or y in the two-dimensional version. You can do x or y in the three-dimensional version, or x in the two-dimensional version, because what we're seeking is some tangent plane or some different derivative. It need not to be respect to x or y or z. Okay, what I'm saying is that you can find if this is 0, it's completely fine. You can show that fx is non-zero. Okay, and then x is locally solvable in terms of y and z. So anyway, it is a graph of some function. That function might be in terms of y and z, or x and y, or x and z. It does not matter. The point is that you know how to do this type of calculation. And so fortunately, we have fz being non-zero. And now we have that z is zxy near this point on the surface, okay? So according to the implicit function theorem, the differentiation with respect to x is minus fx divided by fz. I won't go through the algebra here, but you will simply get 1 over 2 and 2 minus 1. The same thing happens for the differentiation with respect to y, which is minus fy over fz, and you get 1 over 2 minus 1. So for a function z equals zxy, how do you find the tangent plane? We have done this in the previous video, right? It is basically fx, sorry, maybe I should write this, zx, x minus 1, x minus 2, the point, x minus a, and zy, y minus b, and this should be the value of f of a b. In this case, it should be 1, right? So these are the tangent plane equation, and you get this guy. where we know that these two are just constants. So this is actually a linear function. So it's a plane. Okay. Right. So you see that is kind of the powerful idea why the implicit function theorem is so useful. Because in this case, z is actually not really solvable. Oh, sorry, that is not a good phrase. Z is solvable, but we don't know how to present it in terms of, say, ln e to the x or sine and cosine. You cannot solve z in terms of those functions. But it is solvable. There is some function there. We just don't know how to present it. But the fact that we don't know how to present it is not really important. The only thing we need to find tangent plane is simply the differentiation at the point, right? Which can be presented in terms of x and y and z, given the information of this function equation. So to present the graph, this red surface, is the surface given by f of xy being 0, and the 2, 1, 1 is given here, whereas the tangent plane is given by this equation. Okay, the green plane. So we see how to apply this kind of functional derivative, implicit differentiation, that even if you're given a implicit function, you can still differentiate the corresponding variable in terms of the original function. Being specific, I'm saying this formulas, okay? Right, so last, let us remark why is the implicit function theorem, why is the differentiation part in the implicit function theorem kind of natural? So if z is actually solvable on this surface, which is meaning that f of xy is actually 0, then if you want to differentiate back to x, you get by chain rule that you have fx, and then you differentiate this guy by x, right? And then you differentiate this guy by y, and differentiate y by x, and lastly you differentiate this guy by x, and then this whole thing by z, and then this guy by x. So the derivative of x with respect to x is 1, this is 0, and this is actually what we want, right? The differentiation of z with respect to x. So if you solve this, you'll get minus fx over fz, which means that it is natural. And why do we not perform this kind of proof? Because this is not a proof. You see that we assume that z is solvable, right? The part of solvability is actually the most important part, that we can actually construct some function without knowing what that function looks like. That is kind of a fascinating fact. All right, I get that this last piece is kind of complicated and it's very confusing. So try to look it through and understand what this function actually means and how you can apply that to an concrete function like sine, like exponential, x, y, z, okay? So let's go fast. Let's go briefly on what we have done. We have introduced two different versions of chain rule, which is actually the same version, stating that if we're composing some function together with another function, even if it is more multi-dimensional, you can compute the load differentiation in terms of this kind of format. The first term is always the original function differentiated by its variable, in this case, x and y. The second term is a corresponding variable differentiated by their variables, so t or s. That is the two different chain rules here. In this case, it is t and s. And we can generalize it to different dimensions, as we mentioned in this example, okay? And after doing so, we introduce a very important theorem, which is implicit function theorem, basically stating that if you have a function, it might be two variable, then its level surface or level curve or level set, which is f of xyz being 0 or f of xyz being 2 or 3, that is the same thing. Then as long as that the partial derivative of some of a variable at some point is non-zero, then that variable can be locally solved by other variables. In this case, it is y equals to f of x, and you can also solve something like z equals to f of xy. Additionally, not only it is solvable, and that the differentiation of that function is actually computable in terms of the original derivative. So in this case, f prime of x, which is dy dx, is given by minus fx f1. And in the free variable version, dz dx is actually minus fx fz, and dz dy is actually minus fy minus fz. minus f1 is fc. Okay, and we perform two very important example. One is finding a tangent line at some level curve, and one is finding a tangent plane at some level surface. So this kind of algebra and theorem generalize our understanding on tangent planes and tangent lines. You can actually perform those things on different surfaces and different curves whenever they are a function on it. So for example, as I mentioned, z cannot be completely solved here. You cannot write z equal to something in terms of xy, but turns out you can solve the tangent plane at the point, which is sufficient for our analysis of the function. So yeah, that is what we have performed today. Sorry, this might be a long video. Make sure that you done as much exercise as you can do in the chain rule part, because that will be more computationally hard. And I would like you guys to be familiar with this concept so we can perform more differentiation afterwards. Okay, see you guys in the next video.